Hello, welcome everybody to channel Sube. Children, today I am going to discuss question number 49 from the MCQ part of 2019 Physics new syllabus paper. What is the current through the battery of the circuit shown in the figure? Through the battery, so this current, so they have marked it here, so that's what we have to find out in terms of V and R. So let us try to solve this problem. So children, since this given circuit is a little bit complicated, I would like to first of all remind you the lesson, the basic ones, recall or revise. So let us imagine that we have two resistors. We have two resistors like this. So we can connect them, sometimes we can connect them in series. We call, if we connect them like this, just one after another, if we connect like this, this method is called series. We say the resistors are in series. So if we connect the resistors, the two resistors like this, we call that these resistors are in parallel. These resistors are in parallel. So the final resistance we should be able to calculate. Say the value of this one is R and the value of this one is also R. So the final means resultant, equivalent. We say equivalent resistance, that means equal. That means we can replace, for those two, we can replace a single resistor, this one. So the value of that is equal to 2 times R. 2 times R. If we replace a single resistor instead of these two resistors, the value of it should be 2 times the single R, 2 times the value of the single resistor 2R. Say if we have this type of a network, a circuit with two resistors which are connected in parallel, then if we are going to replace a single one instead of that those two resistors, a single one, we should be able to find out the value of that resistor. So that will be R divided by 2. R divided by 2. Because there are two resistors, we take one value and divide by the number of resistors. So number of resistors is 2. If there are three resistors like this also we can connect. If we have three resistors, still we call this connection is in parallel. So in parallel, connections are in parallel. So the value is, final value is then R divided by 3 then, because there are three resistors. So like that, since in our example we got only two resistors, therefore we have to divide it by 2. Value of one resistor divided by the number of resistors. So this is the summary. That is all you need to know basically to solve this problem. So now we have to observe the given circuit thoroughly, examine the circuit thoroughly and find out if there are any series resistors, or any parallel resistors connected to this complicated network. So here we can see this resistor and this resistor is in series, because the end of one resistor is connected to the beginning of the other resistor. So like this, no other resistors, no other resistor or anything connected to this junction. Therefore clearly these two resistors are in series. So the same way these two are also in series. Therefore we can replace one resistor instead of these two resistors and write the value as we learnt now. So 4R, since they are series, in series, it will be the sum of those 4R, that is 8R. Therefore, those instead of those two resistors, we can replace a single one like this, whose value is 8R. And now we have to connect like this. Doesn't matter, color is a little bit thick. Instead of those two, we replaced one resistor. The value we changed, 4R, 8R, so we have written 8R here. Now we can see these resistors are in parallel. These two are in parallel. So instead of these two, therefore we can write, if 8R, 8R in parallel, what is the resultant? Half of each. That means 4R. So we can replace 1 instead of this 2, so I delete 1. So I have to change the value to 4R. And here also 4R. Now that is what we can do from the knowledge just we discussed. So children, now we have to use another theory to solve this problem hereafter. So let us think about the famous story. You must have heard this, but I am going to recall it. The mountain, the story about the mountain. So imagine that there is a mountain. So the height is capital H. So there is a person here who begins to climb up this mountain, and also there is another one here. He also is going to climb up this mountain. So after a certain time, this person, say A, has climbed up to this level, this place. He is resting here after a certain time. So he is at this horizontal level. He is at this horizontal level now. So this person, the other one, assume is B. So he also climbs up this hill, and after a certain time he also approach this level. So now he is here on the at the same horizontal level. So they have to go furthermore to reach the top, this distance. So this one also has to go the same distance. So if these distances that already they have come, this one and this one, are equal, they are equal, and the distance they have to go, that means this part also is same, we say that the potential at this place and the potential at this place is equal. You have to check the total distance. So say this first person has climbed up by now say 1/3 of h, 1/3 of capital H, the height of this distance. Then this person also has climbed up 1/3 of capital H. Then we can say this point is equal to this point potential wise. That means the potentials are equals, because even though I have drawn a line like this, we can't draw a line like this on a real mountain. We can't draw a line like this. We don't know whether these two people are at the same level. So we have to measure the distance, the ratio of the distance that they have already come in terms of total height. That means capital H, in terms of total height. So they have to climb another 2/3 of the total height. So this one also has to climb up another 2/3 of the total height. So if the conditions are like that, that means the distance that they had passed, both of them is equal, and the distance that they have to pass, they have to climb up, is also same like this. Then we can decide that these 2 points are at the same potential, So we have to consider the total length and the length or the distance that already they have passed, both of them. So that is the idea that now we are going to use in this electrical circuit. I think you can understand it. So to apply it here, we have to turn this diagram 90 degrees like this. So we turned this diagram 90 degrees so that this positive terminal of the battery is above the negative terminal, because now we are going to use this line as the higher potential and this line as the lower potential level, because if it is higher, it should be above the lower potential level. Earlier, before I rotate the diagram, if I said this line is the lower and this line is the higher potential, then I don't think you can understand, because the battery positive is that one, battery negative is this one, therefore this one is lower, this one is higher, like this. We can do it without rotating even, but if you have the concept potential is strongly in your mind, then no problem, you can do it. But for everybody to understand, I turn this diagram so that the higher potential is above the lower potential line. So now we can imagine how water flows, is flowing along a mountain to the sea. So imagine now water is flowing like this. So through these resistors means small tubes. So imagine this line, imagine this point, imagine this point, and also imagine this point. Do you think they are at the same potential level? Even though this line is horizontal, we can't say they are at the same potential, because if this resistor is not this value, say this one is 2R, even though in this diagram they look like horizontal, but they are not at same potential if this resistor is this value. So let us check whether these 2 points are at same potential. What we have to do, check whether these parts are symmetrical. These parts are symmetrical. That means the fate of water coming along this line must be equal to the fate of water that coming along, flowing along this line. The fate means the resistance that it feels. So up to this point, the water coming along this line feels this resistance R, and after that, when it leaving this level, it has to feel this 4R and this R. Now keep that in your mind. Then the water coming along, or the current you can say, coming along this line already has to this place, and it felt this value R, the resistance, and it has to feel this 4R and R, the same as right side. And not only that, you have to check these extra sublines also. So while the current is coming like this, some current come and join from here, from 2R. That is the fate of that line. When the current flowing along this line, some current come and join from this 2R, same 2R, that also same. And while it is going along this junction towards this 4R, some current leaks away to this 2R. And this way also, when the current passing this junction towards 4R, some current leaks away towards this resistor, that is 2R. So 2R equals. So the fates are same like that. Therefore, we can decide these resistors, these points are at the same potential. Therefore, equipotential points. So now we decided these points are equipotential points. That means the potential at these 2 points are equal. So if the potentials are equal, we can connect them, because there is no potential difference. Potentials are equal, there is no potential difference. Imagine this battery is 12 volt. Then we can say perhaps this one is at 10 volt. So this one also at 10 volt. The same way, these two are also same equipotential level, equipotential points. So this level may be 2 volt. This one also may be 2 volts. So these two also, therefore we can connect. 2 volt, 2 volt, there is no potential difference. 10 volt, 10 volt, there is no potential difference. There must be a potential difference to flow current. If there is no potential difference, then current is 0. even though we connected these points using a wire or not, no current is flowing. So this conductor, this conducting wire has no current to this way or has no current to this way. There's a wire but no current because the potential difference is 0. So this blue color wire also has no current to this way or to this way because there's no potential difference. So we use this trick now. Therefore we connect and try to solve this problem. Sometimes after connecting like this, but only equal potential points you can connect, then you can simplify the circuit. Sometimes you can simplify, sometimes you can't. So normally in these exams they give the circuits that we can simplify after connecting. So the next thing that I am going to say is, now already I have connected using a wire, but actually without using a wire we can connect these 2 points just dragging this point towards this point and overlapping it and soldering it, or connecting somehow with a clip or something like that. We can connect these points. Somehow we have to connect these points without even using a wire. We can connect. We can drag this point and then drag this node, because these are wires, these resistors are wires, so they bend and let us to drag this point. Doesn't matter, they are wires, they can bend. So now that is what we are going to do. So children, now watch carefully. I am going to drag this point towards this right side point with the resistors, without breaking the connection. So when I drag this point here, I draw it using purple color. Think that this not this purple color. Then I drag this onto this red color node like this. Now it can be seen. So that what happened to the resistor? This junction doesn't get affected because it is connected. So this resistor also doesn't get broken. Therefore it bends only. So like this we can see, after dragging, the connection is here, this connection is here, and the resistor is like this. Now it must connected to this purple color node, to this one. So this part, it is I have drawn bend. It bends like this and is still connected to this purple color. So the same way, when I drag this say this brown color junction or node, brown color node, to this, onto this place and overlap, so we can see the blue color junction underneath. So what happens to this resistor? It just bends without breaking here. So the junction there, the node is here unaffected. So the resistor will be seen like this. It bends towards this side and the value is R. The value of this one is R. So we have dragged both the junctions or nodes. Then what happens to this one? It must move without bending like this towards this place. Like this we can see, after dragging those two junctions, two nodes to right, this resistor also has moved, but not it bent, just the connection is like that. So this is the final appearance. Now we can solve. Because this R parallel, then R by 2, I have to save before. So let us simplify. R are parallel here, then what is the resultant? R divided by 2, half R. So I delete this one because half R so let us write R divided by 2. Here also like that, R divided by 2 because R are parallel. Then I delete this one. Then what do you see? These two we can simplify parallel. Na? Then 4R parallel. Half of each. Then 4R divided by 2. That means 2R. 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 Then I delete this one. Right, let us do this slowly, otherwise you won't understand. So I haven't drawn a resistor here, I have forgotten this one. This one should come to this side, only this node, this part come to this side. This node is not affected, so I draw it now. This node is there, that resistor starts from that node like this, and I will write above to this one. It starts that resistor. This junction I am drawing now. This resistor, it is turned now to right, bend to right now. So the resistor is like this, and is still connected to this brown node, 2R value. Then I have forgotten this one also, 2R, this one is 2R, you see. So you can, you have to draw it. It begins from here, not broken, to that junction, to this same junction, connected like this. The resistor is like this, the end is connected to that purple dot, like this. That is also 2R. And now you can simplify these two also. 2R. What is the value? 2R parallel. 2R in parallel. So the resultant is 2R divided by 2, then 1R. Just R. So I delete this one. Only 1 is there. The value is R. Value is R. Here also the same thing. 2R parallel. The resultant is equivalent. Equivalent is R. Now we have another problem. Furthermore, we can't simplify because nothing we can see series or parallel. This one is not series to this one because there is a sub connection there, subline connected in between these two. So we have connected, we have soldered these for 2 points, remember. Now they are not 2 points, 1 2 earlier, now 1 we have soldered them. We started saying we are going to connect these lines. So now we have to do another trick. Let us discuss it now. Now we have faced the same problem. That means we can't find any combination which are in series or in parallel. This one is a complicated one. So again we have to go to find out, to check whether there are two equal potential lines. So obviously you can say this one is now the lines, this line and this line we can consider. There are two lines. So in these two lines we have to find out two equal potential points. So battery voltage, check it, they have given as V, not 12 volt, I assumed it as 12 volt, they have given as V, battery voltage is V. So if these resistors are equal, RR, how the voltage across these resistors appear? Here we divide by 2, that means half V. Here we divide by 2, because totally these two lines, between these two lines there is a voltage V. There is a voltage V. So it is divided between these two resistors because they are equal. So the voltage also must be equal. Therefore we must see that. We must see that. So since this total voltage is V, now total voltage is V, we can divide it between these equal resistors, half V to each, half V to each. So here can we take this point as half V, this distance from the bottom? Do you think this voltage is half V? To be half V, that point to be half V, since the below resistor is R divided by 2, this total resistance should be R divided by 2. But it is not here now. There is another, this 2R. So therefore this one is not V divided by 2. Then do you think this junction, this node is at half V, this distance? You can't think like that, because you can't take it like this, because as half V, because this distance is 2R and half, 2.5 R, that is longer. Go to the story of that mountain, this distance is longer, this distance is very shorter, R divided by 2. So we can't say half V, half V. Therefore we have to do a little trick, because we know that this point is at half V. We divide by 2 from the below, from the bottom line. From the bottom line we know the height is half V, because this total height is V. This total height is V, that gives by the battery. So since these resistors are equal, the total distance, total height must be divided into 2, and that is why we say that this distance is half V. This height is half V. So therefore this point is at half V level, positive half V, because from the below, from the bottom we go upwards. Upwards means we are going to the battery positive, we are going to the battery positive line like this. So we are going to the positive region. We are going to the positive region. Therefore we say this point is at half V positive. Then we can divide this 2R into split into two parts like this, because the problem is there. I do like this, I keep this aside and I take this half like this, and I take this half, then RR, because totally 2R, now RR, then I destroy these wires, or I can bend and connect like this, and there is a node now here, node. This one is now R, this one is now R. Totally it was earlier 2R, now I have split into 2. Now what is the, what you can see? Don't you see that this place is half divided like this? The total height is divided into two parts, half R and R. You meet this place now. Again you have to go upwards, R and half R. Half R and R, then R and half R, same. So therefore we created the half volt, half V point like this, using that trick. Now we can solve this easily. So this point now you can say V divide by 2 from the bottom, from this bottom line. The voltage is V divide by 2, the other V divide by 2 is here, because the resistance must be equal, or the ratio must be equal. So here R and half R, this upper side also half and R and half R. So this one is the center. So now you can either connect these points, or this you can connect these points, this point and this point you can connect by a wire, or drag and solder, you can do anything. So I am going to drag this point now, drag this point, let us use a color, this node over to this red color node, connect by dragging. So drag this to this place and connect with that red one. So now I am going to do this blue color, the node is now here, I have already dragged. Then what happens, these wires bend like this, connected, or connected is still like this. Now you can shorten these wires, taking this resistor a little bit left. I am doing all these things for you to understand, otherwise you don't have to do all these things. So I try to do it. So this resistor is connected with the long wire, you see. I can shorten it like this. First of all I delete it. Remember the resistor is there. These unnecessary wires I delete and use as short as possible. This one is the now resistor R. So I will do the same thing to the above this resistor also. Unnecessary wires are there. I shorten the wires and connect the resistor like this. Just take the wire and the resistor here, connect to this node. So R and R there. Now what do you see? Do you see any relationship? Yes, these two are parallel, and these two are again parallel, because the junction, the ends are connected together the same way as in a parallel circuit. So these two are parallel to each other. Therefore, R parallel. What happens? R divided by 2. R divided by 2. So I delete one. Then I left one to be there. So R divided by 2. So this one also I am going to delete, and instead of these two, R divided by 2, a single resistor is then there. So let us draw it. R divided by 2. Now these two are series. R divided by 2, R divided by 2. Then R. Then R. R, single one. We can draw a single one. Say like this, R. Then these two also are in series. Again we can delete, and we have to save. So we were going to write the equivalent resistor for these two. R divided by 2, R divided by 2 are in series. So R. So R. So let us write 1 R. Let us draw 1 R here. And now these R are in parallel. These two also are in parallel. So we can write R divided by 2 instead of these two, R divided by 2 instead of these two. Then let us delete this one. Now already finished. Now what can we do? These two are in series. Half R, full R. Then we can delete one of these resistors, any one, and instead of that we delete divide by 2, only R. So the final resistance is R. Final equivalent resistance is R of all those big network. The final resistance is R. So now what we want is the current. So they have given the voltage here is V from the battery. So now V equals IR. So the current is just V divided by 1R. That is the answer. V divided by 1R. This one is the answer. So children, the fourth one is the answer. So now I think you could understand. If you have never solved these types of questions, now you will be able to try, because I did it very slowly with using colors, and you know, you see, actually really I tried to teach you, just not to show you that I know this. I tried to teach you. So I think you are happy. I will be happy if you subscribe my channel. So meet you tomorrow. See you tomorrow. Goodbye.